Okay, this is the fourth video in the series. We are creating a physics engine. It's the simplest form of a physics engine, just about as simple as I could think of. We are modeling the physical properties of the world, a subset of them. We are modeling velocity and position, and that's just about it. So to take a look at what we are trying to make, this is the completed solution that we're shooting for. We see these circles have a velocity. Some of them are faster than others, right? Velocity has a direction, right? And then there is a position. Obviously, each one of these has a position, and we modify that position based on the velocity. And so the last item that we kind of have to add here is the collisions. So this is what we're shooting for, and this is what we have currently in Python 3, part 3. So this is what we left off with last time. So we're close. We have all the circles. All the circles have velocities. We basically just need to add that collision aspect, and this is one of the trickier parts. We're going to run into a couple issues as we code this. So it might be good to get a pen and paper out, and it's not hard math. There's a little bit of math, but it's the most difficult thing is you have to conceptualize what's happening, right? And then try to model that with computer science, right, with your code. All right, so we'll use some images and try to model that out, okay? So looking in the code, what did we do last time? We made draw background. It had this clear. We put that in there to clean up our animation loop. We want to keep this animation loop relatively small. We want to be able to figure out what's going on, what are the steps going on in our animation loop, right? So we cleaned up the code a little bit. We abstracted away from the concept of one circle to many circles. So we create all of these circles here. This is a list of circles, and in a for loop, we add these circles, right? So these circles are just dictionaries. Create circle is a dictionary, and we get some random integers for the x and y value, random integers for the radius, and for the velocities, and then we also get random integers for the color. Okay, and so when we say create circle, we really mean a data structure that holds all of the physical properties of this circle, right? So we're using a dictionary. It would probably be better if you're a little bit more advanced to maybe create a circle class that has all of these properties, right? But again, I wanted to keep this accessible to beginners. So one of the things we talked about last time is this concept of an interval. Now this interval, again, this is very important. This is the amount of time since the last iteration of this loop, right? So this is the time between frames. One iteration of this loop, this animation loop, is generating one single frame, right? We know, like in an animation, it's one frame, and then that shows for just a second, and then not even a second, but a very small interval of time, and then it's erased and a new frame shows up, and it's erased and a new frame shows up. And you can see this when you have a pad of paper and you draw little pictures on it and flip through it, right? It looks like it gets the appearance of motion, right? So that's what animation is all about. So this time interval is very important. This time interval, what is the unit on it, right? This is seconds, but this is the number of seconds it takes per frame, right? So if we put this in context, interval is definitely seconds, but it's seconds per frame. Now what is frame rate? So if you play any video games or you're into high quality video or anything like that, you always have this concept of FPS, frames per second. Okay, that tells you how many frames are going across the screen in a given second, right? And the eye can detect low frames per second, right? But if you get very, very high frames per second, like between 30 and preferably like 60 for high quality video games and video editing, 60 frames per second or more is fast enough where the eye can't really detect a difference. There's no jarring motion. All right, so frames per second. Now the interval is seconds per frame. All right, this is the number of seconds per frame, and if we want frames per second, that's just the reciprocal of this, right? So we could say FPS, frames per second, is just 1 over our interval. And what we can do is we can print this out each time through the loop. So as we run this, we can look over here and it's going to print out our frames per second. Per second. All right. So let's, well, actually, let me copy this, and I'm going to undo and go back to where we were, because I need to duplicate the file. Alright, so that was part 3, that's where we left off. So before I change anything, I want to make sure I duplicate this file. Let's make sure I didn't break anything real quick. Alright, so that was part 3. So I was just going over part 3 there, and now we duplicate and we go to part 4. That way, if we ever need to go back to part 3, it's there. Alright, so here's where I added the new stuff. We say frames per second equals 1 over the interval, because this is seconds per frame. Right, so the reciprocal is the frames per second. Print FPS. Alright, so let's take a look at what this looks like when we run it. Part 4. Drag this over. Okay, and see over here we're printing out our frames per second. This is pretty smooth. When you're watching the YouTube video, it might look a little bit jerkier because the YouTube video also has frames per second. So even if the quality here is high quality, it's frames per second, we also have another layer of frames per second going on with the video. So it might not be as smooth as, like if I say this looks really smooth, it might not look quite as smooth to you, and that would just be because of the video. But this is proving what our actual frames per second rate is. Okay, so notice we have I think 10, let's go to the top and see how many, we have 20 circles here. All right, so notice that was about 30 frames per second. Well, one of the things that's going to make this whole loop take a little bit longer is this delay at the end. So we are delaying 1/100th of 1 second, right? So even if this executed in instantly, right, we would still have this delay of 0.01 seconds, right? So the reciprocal of that, let's see, 1 over 0.01, right? We can use Python, and 1 divided by 0.01, right? That's 100 frames per second, right? Even if all of this stuff happened instantaneously, okay? So if we make this delay smaller, let's make it 10 times smaller, then our frame rate should go up. And technically you don't necessarily have to have this time .sleep here at the end, but it's kind of nice to adjust and play with the frame rates. And if you make it small enough, it's sort of negligible. All right, so here we're going to see part 4. And our frame rates have gone up. All right, so we're at 40, 45, something like that. Now if we exit this program, let's go back down to maybe 10 circles. Now we've got really high frame rates. Right? So the more activity, the more objects, the more action, the more animation you have on the screen, the longer it takes to update, right? And so this is not only drawing items, but it's also maintaining their positions, right? And also, again, Turtle Graphics is not ideal to be building a physics engine with, right? There's performance issues that Turtle Graphics is keeping track of a whole lot of information that we don't necessarily need in the background, and so that's causing a delay as well, right? So you would actually want to choose a library that was designed to build physics engines with something like that. So, but the whole point of these videos, this series of videos, is to show you, the concepts behind what a physics engine is and sort of what goes into the basics of it, right? So we got this concept of frames per second. And we can see we might be able to get that up even more if we change this delay. This probably won't make a difference because our delay is pretty small. Once you get to a thousandth of a second, this would be a 10,000th of a second, and now it's pretty negligible. So let's see if that makes any difference. A little bit, not much, right? But extraordinarily high frame rate right there. Okay, and so then as we go up, I'm going to go back up and modify the number of circles. Okay, so here we're going to say we have 50 circles. All right, we're going to run that, and we're going to see how much this affects our application. All right, so my computer here. There we go. It didn't like something, but that's fine. This should still work. So I'll run this again. Part 4. Right, and so when we increase the number of circles, our frame rate dropped significantly. All right. I'm going to fix my displays. For some reason, they reset in the middle of that. All right. So, what we need to look at now, that's the completed version. So, here, let's clear this, run it one more time, part 4, there we go. So these are our frame rates. We go back up to the top, number of circles, we'll put that back down to 20, and we'll see our frame per second should increase with decreased activity, decreasing the number of things we have to keep track of, the frame rates will go up. All right, so we'll close that, run it one more time. All right, and they more than doubled, so that's good. So that's frame rate. Let's move on to probably the hardest part of this is going to be the collisions. All right, so how do we model a collision? Right, if we look at and where do we add that code? Right, so what constitutes a collision? If we look at this sort of diagram, let's think of one of the balls or one of the circles going up and hitting a wall. Right? It hits the wall. Now, what we want to do is we want to detect if the center point is beyond the wall. If it is, then we're going to reverse so if the wall is vertical, right, that would cause the x direction to be reversed. Right? Same if it was coming in from this side. If we go beyond the border, then we would want to reverse the direction. Right, so that's going to be the first step, and we're going to see that that sort of works, but there's some issues with it, and we're going to come back to this this diagram. When you're modeling things in physics, when you're modeling anything with computer science, it's handy to have drawing tools or a whiteboard or something like that, and make these diagrams and make calculations. Okay, so here we go. We're going to have to do this in the update positions area, right? So in the update position. Right now, I believe, let's see, where is it? There it is. The update circle. There's not much in here, right? We're just calculating an x and a y, right? But now what we have to do is we have to say, wait a minute, if this x is past a boundary, right? So what does that mean? All right, so first, let's check the x direction. Okay, so if circle x, this is the x position of the circle, if this is greater than the maximum value of x, so what's max x? So that's back at the beginning, we defined these constant variables. Maximum x has to do with the size of our window. The maximum x is the x value all the way to the right of our window. right? So what we could say is if the circle x is greater than max x, then we'll say circle velocity in the x direction needs to go in the opposite direction. So how do we do that with a quantity? What's the opposite when we're talking about modeling this? Well, that just means instead of adding whatever the velocity is, if the velocity is 10, we're adding 10 pixels every time. Well, if we're going in the opposite direction, we're just subtracting 10 pixels every time, right? So basically what we want to do is just multiply whatever the velocity is by -1. That will negate it, right? So it's whatever it was before times -1. That's what that syntax means. Times equals. It's the same as saying equals whatever it did before. Circle the x times -1. Right? This is equivalent to this syntax. Right? Times equals. So this just flips the direction of the velocity. So if our circle value x is greater than the maximum, so if we have our window here and the x value has gone past our maximum, then we flip the direction of the velocity, so it'll bounce back the other way. And this is just with respect to x. All right, so we need to do that with y as well. So if circle y, or sorry, actually we need to finish x. So we just did the right-hand side. So else, elif, circle x is less than the minimum value of x. Right? So the maximum value would be on the right, and the minimum value would be on the left. So if our x value is less than this minimum value, then we know we've gone past the boundary there. And so we would also times equals -1. All right, so now we could see that we could join this logically. We could say if circle x is greater than max x, or if circle x is less than min x. We could join this all in one Boolean statement. But as we progress, we're going to see we're going to need these two separately, right? So this, if we just do this by itself, we should get some form of bouncing off the wall. It's not going to be perfect yet, but it's going to be bouncing in the x direction. We haven't implemented the y. So let's just take a look and see what we have so far. Right, so we see some bouncing. Now notice where it's bouncing though. Right, it's bouncing from the center point of the circle. Bink. Right? Bink. So that's because what our logic is doing is taking the x value of the circle. That's anchored in the center of the circle. So when we say if the center of the circle, the x value of the center of the circle is greater than max x, right, then we reverse. So what we really want is we want to know the edge of the circle, right? So what's the edge of the circle? So if the circle value, the center of the circle, plus its radius is greater than the maximum x value, and then on this one it's going to be the circle x minus the radius. Right? So all this is going to do is just shift this number by the radius. So that way, when we have a collision, it's going to be the edge of the circle instead of, see that? The edge of the circle. Now see that anomaly right there? That tells us we're not modeling the physics exactly right. So you'll see that sometimes they stick, and we have to think about why that would happen. Okay, so those anomalies we have to take care of. All right, so let's close that. All right, so why would that stick? And you see it is moving a little bit. It's like vibrating back and forth, right? So if we look back at our picture of this wall collision, what could be happening is that here's the boundary. The the ball is moving beyond the boundary, and so we flip the direction, right? But then the next frame happens to take less time than the previous frame, and so the ball does not move past the boundary, right? So the ball is moving, and all we do in our code right now is just once it's passed, we flip the direction. What we really need to do is if we've moved past the boundary, that means we collided sometime back in the past. And if we collided sometime back in the past, then we should bounce off that point where we collided, right? So this distinction here is causing the problem, right? We have a ball moving towards the center point, towards a wall, right? And in our simple model, we just have the ball not actually bouncing at the exact correct location, right? It's kind of hard for us to tell because we're talking about such small distances, small pixels, but the computer can tell. So if in one frame I move past the boundary and then I reverse direction in the X, right? Then this ball will be here and it will just start moving in the X. But if that last frame was quicker, then I would have traveled less, and the ball will still not make it past this boundary. So then it reverses direction again, and then reverses direction again, and eventually it can come out of it. But it all depends on how fast the computer's running and how fast the frame rate is. So this is a faulty physics engine for that reason. We need to take that into account. We have to be more precise with how we're dealing with the actual physics, what would actually happen in the case of a collision. So what we need to do is sort of calculate this overshot. How much did we overshoot the position here, right? And then we need to whatever we overshot in this x direction here, we need to subtract that from our position, right? So if our position is here, how much did we overshoot? Then we need to subtract that, right? And so if we have some value here we'd want to subtract, it would be 2 times the overshoot. So if our overshoot is this amount in red in the x direction, right? And this is our current x position, we want to subtract that amount of red, right? So subtract the overshot, but then we'd also have to subtract another overshot. So 2 times the overshot. All right, and this is exactly where these diagrams become helpful. You really have to think about what's happening and then try to translate that into the code. All right, so what does that look like? Here we have circle x plus the radius, right? So if this is greater than the maximum x, so that's detecting the collision. We need to calculate how much we overshot. So this one is a collision with the right-hand wall, the maximum x. All right, so what is our overshot? Well, our overshot is going to be basically the difference between where we are, that's circle x plus the radius. So the overshot, circle x plus the radius, we're going to subtract the maximum x value. So this is where the edge of the circle is past our maximum value. So minus max of x. Now, there is a lot of math here, but it's really simple math. You do have to keep track of it, right? X is the center of the circle, so then we add the radius of the circle. So the right-hand side of this circle, this is this position, and if we subtract the maximum value of x, that's how much we will have overshot. So then what we want to do is we want to adjust. We want to say circle x, we should subtract two times the overshot. All right, so we can just test this one. So we're going to be looking at the right hand side. So we shouldn't see any of that vibration anymore on the right hand side. On the left hand side, we still might. We still probably will, right? Okay, so good bounce. Okay, so we're not guaranteed to get that behavior, but we just can. It sort of depends. So let's try to add more circles and see if we can get it to mess up on the left-hand side there. So let's go back to 50 circles at the top and test this. So yeah, here's that behavior. But we don't see it on the right. We haven't seen it anywhere on the right yet. So it looks like this is solving our problem. We just need to apply it to this side, and then we need to have the collisions at the top and bottom. Okay. The nice thing is once you solved it on one side, you pretty much know how to solve it on the other sides, right? So basically for every edge, we need this, right? And obviously for the y direction, we would change that to y, right? That sort of stuff. So here, we have to calculate our overshot, and then correct our x position. So what's the overshot in this case? This case, we are looking at the left-hand side, and if the circle minus the radius, so that's the left-hand side of the circle, if that is less than the maximum value or the minimum value, right? So overshot equals. So this is circle x minus the circle radius. So that just means this is just the position, the x position of the left-hand side of the circle, whereas if you add the radius, that would be the x position of the right-hand side of the circle. So this is the left-hand side of the circle, and if that is less than our minimum value of x, or I'm sorry, we subtract from that the, see, would we subtract or would we add it? So the overshot is the amount we've moved past, right? And we're going in this direction. So the left-hand position, and if we subtract the minimum value of x, right? So this is again where the diagrams help. So here we're coming this way. If the left-hand side is passed, so this is going to be a smaller number than the wall on the left-hand side. So this smaller number minus this bigger number, but it's still negative, right? We would basically be adding that number, and we'd be left with a negative overshot, right? So our overshot here, this would be a negative value, right? So then we would want to update our circle x position, and we're going to say that this equals whatever it did before, and we want to basically do the same thing. We're going to subtract 2 times the overshot. Now this works because overshot is negative in this case. Up here overshot was positive. We overshot up to the right. We overshot a certain amount to the right. Here we overshot a certain amount to the left, which is negative. So 2 times the negative, but we are not, if we subtract that, that's actually adding the value, so that's going to move it to the right. Here we're subtracting the overshot, which is going to move it to the left because this is positive. Subtracting a negative number is adding, so it's going to move it to the right. Okay, so again, this this math isn't complicated, but it's just enough where you need a diagram or something to really think through what's happening, like even the position of the circle, and then subtracting the radius will give you the left-hand side of the circle, and adding the radius will give you the right-hand side. Those simple concepts, translating the physics of the numbers to what that translates to the actual model that you're trying to replicate on with computer code. All right, so this should appropriately fix our collisions for the x direction. And so I don't see any of those bouncy back and forth type collisions anymore. And this is a better model of reality, right? The more details we add to the code, the more the better the model is, right? And that's the whole point. We're trying to model reality. That's why it's called a physics engine. All right, so now this we've taken care of the x, and there were two cases, right? There was the right-hand side and the left-hand side. So now we just do the exact same thing for y, really. So I mean, we could copy all this code and then just make the appropriate changes. Right? So anytime we have circle x, we're talking about the y direction now. So all of those should be y. Anytime we have circle x, we're going to change that to a y. We have vx, that's going to be vy, x, x. Right? There's all those. Anytime we have max x or min x, that should be the y value as well. Right? So this max x should be max y. This max x should be max y. Screen displays are messing up again. I think the cable in the back, my cat messed with it. So let's move this one back. All right, here's where we are. Max x should be max y. Max y. This min x should be min y. And that min x should be min y. So we'll make those changes, and we should be pretty close to being complete. So any other usages of y? Right, so what we just did here, the copy and pasting, it's a little risky because we're not walking through the code logically. You might want to do that for sure. Like make sure that this is doing what you think it is. So the way we did this one is we walked through it logically. We had a diagram and we figured that out. Here we're kind of taking a chance. We're trusting that if we change all these values to y, it should just work. So we can go ahead and try this, but you might want to, in reality, you would want to go through and logically test all this. In the interest of time, I'm kind of skipping over that step. All right, so let's see if I can find, there we go. So it looks like all of our collisions are working. We've got frames per second. There was a sort of strange thing that popped up with scroll bars. I'm not sure why. So let's try that again, and that might have just been something strange on my machine. Yeah, I think it's just because my display's messed up. My displays again. I think that's just from a loose cable. Apologize for that. Yeah, now the scroll bars are gone. All right, so we see we have collisions happening, and there were some glitches, right? And honestly, there's going to be other glitches. We haven't perfectly modeled reality. One thing comes to mind. Let's say we have a circle that's going very, very quickly. Like right now, our maximum speed is 100 pixels, right? Let's say we have something moving at 500 pixels or 1,000 pixels per second, right? We do the calculation, and the circle crosses this boundary and winds up way over here somewhere, right? And then we fix that, but it crosses the boundary, but it also crosses the y boundary. So if we fix the x, it would still be across the y boundary, and we'd still have some issue. Right, so the reality is, with collision detection, you want to detect the first collision that happened, but in that same time frame, there might have been a second collision as well, and then you would need to check for collisions again. So you have to go through and repeatedly check for collisions. If there was no collision, it's easy. you're just done. You update the position. But if there's a collision, you have to calculate the new position and then also check for other collisions. So this gets really complicated, especially if you were going to make all of these circles collide with each other. Now, it is possible. It just, you really have to think through how that would work. All right. So this is basic physics engine. You know, you can work with this to make whatever you want. You could start making a Pong game. So you could think that the next step for you, if you wanted to work on something on your own, might be, you know, put a vertical line in the middle or imaginary line or whatever, and have all of the circles on the right hand side bounce off that one over here, and all the circles on the left hand side bounce off that one and end up over here. Then what would be slightly more complicated is if you had a rectangle in the middle and have any balls, they would bounce off the sides of the rectangle, and say they'd just bounce around. And if you got that going, then you could make a Pong game. You could put a rectangle on this side and a rectangle on this side, and you would have to try to figure out how to make the rectangles move. But then if there's a collision, then you would make the balls move, and you could have ping pong, basically, right? So you see, this is the very basics of a physics engine. It is, you know, it's not a ton of code. For a beginner, this is quite a lot of code, right? But it's enough to get you understanding all the principles of, you know, what is it when people say the words physics engine, what is frames per second, you know, what is, how does animation work, right? So all of this sort of ties together, and it's really interesting. It's kind of a lot of work for a beginner, but it's not a whole lot of math. It's just math that you have to be careful with. You have to think about a little bit, right? So it's just adding and subtracting and trying to figure out, you know, what these locations are that we're talking about, translating the actual model into math. All right, so that's a big part of computer science. So hopefully you enjoyed this. I'll scan through the code one more time. Draws a rectangle, draw background, create circle. That's drawing the circle. And this is probably the most complicated thing. This is what we added this time. We updated the circle, and these are the collisions. Right? So this is the collision of the x direction. These are the collisions in the y direction. Right? And then the other thing we added here was just the frames per second. And that frame per second is just the reciprocal of the interval. Right? So again, hopefully you enjoy this. Hopefully you learned something. And have fun with it. Play around with it and make it better. Thanks for watching.